Hello, welcome back. So today I'm going to talk about some important aspects of physics that we need to understand in order to proceed with what we're going to do. In this example, what I'd like to say is the following: that there were people that worked on understanding the physical world, 300-400 years ago, that were able to deduce very important aspects of the world from very limited information. In a sense, that's what makes it so remarkable, is that they were able to glean extensions of their ability to see things in front of them simply by sheer force of will, more than anything. So one of those things that I've written here on the board, and we're going to go through, is the first law of motion that's attributed to Newton. Galileo was important in this as well. He developed some very fundamental understandings of planetary motion through the use of telescopes, but we always ascribe these sorts of things to Newton. There were lots of other people, of course, working at the time to try and understand these things, but they have been codified and associated with Newton. So I'll just read this and you can think about it. All bodies remain at rest or moving with a constant speed. We'll have to define these terms, so this is a term we're going to define. Constant speed and direction until compelled to change that state through the action of an outside force. Now, these are important attributes that we're going to go through and talk about. This idea of being compelled by an outside force means that there has to be some sort of important thing that changes how something is moving. And that comes through an interaction. Interactions are essential to this course. We're going to talk about how interactions work. So let's say I have a particle. Let's say it's a charged particle, a positively charged particle, plus, and that particle moves like this, such that the end, it's over here. What has changed? Well, of course its direction has changed. Perhaps its velocity has changed. Perhaps there are other things that change about it as well. But what caused it? Why would it do this? Without any context of what happened in this region of space, we don't know why. But we know that there's an interaction. Something has changed. We can say that some things may change in a way that we can directly see. So I'm going to show you a sort of set of clips of a particle. And I'm going to say that this is its time t1, this is its time t2, this is its time t3, this is where it is at time t4, t5, and t6. All of these time points are equal in time. That is, delta t21 is equal to delta t32 is equal to delta t43, etc., etc., etc. But delta x, call this 1, 2, 3, 4, 5, 6, delta x21 is not the same as delta x32 is not the same as delta x43, etc., etc. So what's changing? In these intervals, the distance is changing, but the time interval is staying the same. So that means that this is changing its speed. In one dimension, we say that the distance has changed, but the delta in time has not. So if I look at the ratio of delta x to delta t, this is going up. It's increasing. And so that means there's an interaction. Something is happening. Okay. So we need to have a language in order to do this. One of the pieces of language that I need to introduce is the idea of a velocity. What is velocity? Well, it's a vector. So let's write down some things. Vector. So a velocity is a vector. So I can draw a vector and call that a velocity. Here's a velocity vector. There's my velocity vector. I can have two things associated with this vector. A velocity represents two things in particular. That is a speed. So, for example, if you're in a car, your car says you're going 55 miles per hour. That's your speed. So 10 kilometers per hour, let's say. Let's use a slightly different set of units. So those are the units. Let's say kilometers per hour or meters per second. So this would be, I don't know what the conversion is, but let's say 15 meters per second. Okay, those are the units of that. So speed tells you something about how fast you're changing your position in time. It also has a direction. Well, if I'm going 55 miles per hour, that doesn't tell me anything about where I'm going to end up after going for an hour. Am I going north? Am I going east? Am I going south? So direction also matters. So direction tells me which way I'm going. Okay, well that's good. This is if my speed or my direction don't change, so no change, then I have uniform motion. That's what we call it. There's another aspect to uniform motion that we often overlook, and that is not moving. Velocity equals 0 is another type of uniform motion. So sitting still is important as moving in that context. So uniform motion is what was written in Newton's laws. And so no change in speed or direction is what's important to Newton's law. We state that if something's speed and something's direction is not changing, then it's undergoing uniform motion and there's no outside influence. There's no external force moving that object to change its speed and its direction. So something being at rest obeys that law as well, and something moving at the constant velocity of whatever that velocity it could be the speed of light. Constant velocity. Moving with a constant velocity implies you have no external force acting on you. Okay.